Have you ever just looked up at the night sky and thought about that silent, perfect dance of the planets? I mean, they move in these gorgeous, predictable paths, and they never seem to stray, they never stop. It's like a cosmic ballet on a scale that's almost impossible to wrap your head around. But what are the unseen forces conducting this whole symphony? Well, today, let's unpack the physics behind one of the most elegant concepts in the entire universe: how orbits actually work. For as long as we've been human, we've been completely captivated by this. I mean, ancient astronomers, philosophers, they all mapped the stars, trying to make some sense of it. They could see the order, they saw the predictability, but what was actually going on? The why behind it all was a total mystery. And really, this is the big question, isn't it? When you think about it, everything should be doing one of two things: either getting sucked right into the massive gravity of the sun, or, with all that incredible speed, just flinging itself out into the cold, empty darkness of space. So, what's the secret? How does the universe walk this impossibly fine line? Well, the answer is a perfect cosmic balancing act. It all comes down to two fundamental forces. You can think of them as the two main characters in our story, and they're constantly playing this epic game of cosmic tug-of-war. So, let's meet them: inertia and gravity. Okay, so first up, you've got inertia. Think of it like this. If you're on a skateboard and you get a good push, you're just going to keep gliding in a straight line until something, a crack in the pavement, the curb, whatever, stops you. That's inertia. It's an object's tendency to just keep doing what it's already doing. And on the other side of the rope, you have gravity. That's the universal force of attraction, right? The constant pull that every object in the universe has on every other object, always trying to pull them closer. In orbit is what happens when these two forces are in perfect harmony. The planet's inertia is constantly trying to send it flying away in a straight line, but at the same time, the sun's gravity is constantly pulling it back in. The result of this cosmic arm wrestle? The planet is always falling toward the sun, but because it's moving so ridiculously fast sideways, it perpetually misses. It's in a state of continuous, never-ending freefall. So how in the world did we figure all this out? For centuries, this was one of the biggest puzzles in all of science. So let's jump in a time machine and meet the guy who first started to crack the code. Not by guessing, but by looking really, really closely at the evidence. Okay, so the stage was set by pioneers like Copernicus, who had this crazy idea to put the sun at the center of the solar system. Then came Tycho Brahe, an astronomer who was just obsessed with precision. He spent decades, meticulously recording the exact positions of the planets, creating the most accurate set of data the world had ever seen. And then he handed all that precious data to his brilliant assistant, a man named Johannes Kepler. Now, Tycho gave Kepler a very specific and notoriously difficult job: figure out the orbit of Mars. For centuries, pretty much everyone just assumed orbits were perfect circles. I mean, it seemed like the most perfect heavenly shape, right? But Mars just wouldn't cooperate. No matter how Kepler crunched the numbers, he could not get Tycho's super precise observations of Mars to fit into a circle. The data was screaming at him, telling him something totally revolutionary. And by trusting that data over thousands of years of belief, Kepler made three incredible discoveries. First, he realized orbits aren't circles at all. They're ellipses, kind of like stretched out circles. Second, he figured out that planets don't move at a constant speed. They actually speed up as they get closer to the sun and slow way down as they get farther away, kind of like a figure skater pulling in her arms to spin faster. And third, he found a precise mathematical link between how long a planet's year is and how far it is from the sun. It was all a beautiful mathematical system. Now here's the crucial thing to understand. Kepler had perfectly described what was happening. He laid out the rules of the road for the planets with unbelievable accuracy, but he had no idea why. What was this invisible force that was yanking the planets around, making them speed up and slow down and follow these weird elliptical paths? The answer to that question was going to take another scientific revolution. And the person who answered it was, of course, Isaac Newton. About 50 years after Kepler, Newton was the one who connected the dots between the laws of motion, right here on Earth, and the grand movements of the heavens. He finally gave us the why. Newton started with the law of inertia. That's the same principle we talked about earlier. He realized that a planet, if you just left it alone, would shoot off in a perfectly straight line, forever, into the void. So that explained the outward part of the equation. But what was the mysterious force pulling it inward? And this right here is the stroke of pure genius. Newton's great aha moment was realizing that the force pulling an apple from a tree down to the ground was the exact same force that was reaching out across 250,000 miles of empty space to keep the moon locked in its orbit around the Earth. It wasn't some mystical celestial force, it was universal. He called it gravity. To help everybody else understand this revolutionary idea, Newton came up with one of the most famous thought experiments in all of history. He said, okay, imagine a cannon, and it's sitting on top of an impossibly tall mountain, so tall that it pokes out above Earth's atmosphere, so there's no air to slow anything down. All right, so you fire the cannon with a little bit of gunpowder, the cannonball travels a short distance, and gravity pulls it back down to Earth. Boom. Simple enough, right? Now, you pack in a lot more gunpowder. You fire it much faster. This time, it travels way farther around the globe before it finally lands. But then comes the magic moment. If you could fire that cannonball with just the right amount of mind-boggling horizontal speed, something incredible happens. The cannonball starts to fall towards the ground, but it's moving forward so fast that the Earth's surface curves away from it at the exact same rate. It is constantly falling, but it never ever lands. It falls all the way around the Earth. It has achieved orbit. And that thought experiment, that is exactly what's happening with our moon right this very second. The moon's inertia is its natural tendency to just fly off in a straight line, but Earth's gravity is constantly grabbing it, yanking it inward, bending its path into that stable orbit. It's Newton's cannonball, just on a much, much grander scale. Now, these discoveries from hundreds of years ago aren't just cool historical facts. They are, and I mean this literally, the foundation of our entire technological civilization in space. Think about it. Every single artificial satellite we have up there, the ones for GPS that get you where you're going, for weather forecasting, for global communications, for science, every one of them operates on these exact same principles. Each one is a tiny human-made moon placed into orbit by perfectly balancing its speed against Earth's gravitational pull. And that's what makes our connected world possible. We've gotten so good at this dance that we don't just fight gravity anymore, we actually use it to our advantage. There's this cool technique called a gravity turn. A rocket launches straight up to punch through the thickest part of the atmosphere, but then it starts to tilt, and it literally lets Earth's own gravity pull its path horizontal. It's a brilliant move that saves a ton of fuel that's needed for that final big push to get up to orbital speed. And you know, it's a really common misconception when we see astronauts floating on the International Space Station that they've somehow escaped gravity. The truth is, the force of gravity up there is still about 90% as strong as it is right here on the surface. The reason they float is because they, the space station, and everything inside it, are all in a constant state of free fall, perfectly balanced by that incredible orbital speed. They are, all of them, Newton's cannonball. So, from the graceful dance of the planets to the satellites that power our modern lives, everything is held in place by this delicate cosmic balancing act. It's a simple, elegant balance between the tendency to fly away and the force that pulls things together. This fundamental principle literally built the architecture of our solar system, which leaves us with just one question: what will we build with it next?